Now we are going to see how Fermat's theorem can be used to build a first cipher. We'll start by reminding that Fermat Theorem says a at power p minus 1 congruent with 1 mod p for p prime. And we already mentioned a generalization of this in our exercises. We have discussed a generalization to a at power a multiple of p minus 1 also being equal to 1 congruent with 1 mod p. We have talked about another generalization where we multiplied on with a on both sides of the original format, and we are getting a at power p congruent with a mod p. What would be a nicer way to get this exponent this generalization used for higher versions of values of the exponent? So one attempt could be to try to raise this at power k and to say a at power k times p congruent with what? It would be to a at power p. That would not be equal to a. That would be less interesting. So rather than raising this to power k, we'll start from this generalization here, multiplying it with a, and we are going to get a at power k times p minus 1 plus 1 congruent with a mod p. This is more interesting, and it has multiple applications that we are going to see from now on. One of them is for encryption. Let's see a numerical example with 3 at power 10 mod 11. We know that 11 is prime. We know that 3 at power 10, which is 11 minus 1, is equal to congruent to 1 mod 11. And its generalization that we have seen before, when we raised all these relations to the power 202, we are getting 3 at power 2020 congruent to 1 at 2020, which is still 1 mod 11. Now the second generalization here stands for 3 at power 11, raising this one, multiplying this one times a, gets 3 at power 11 congruent to 3 mod 11. But obviously 3 at power 22 is congruent to 3 at 11 times 2, which will be 3 times 3 different from 3 mod 11. Right, so this is not an interesting relation. This one is nicer. 3 at power, we multiply with a on both sides, with 3 in this case. 3 at power 2021, congruent with 3 mod 11. And this is because 2021 is 10 times 202 plus 1. And that's why we can reduce it to 3. This kind of generalization of Fermat Theorem can be used, and we'll see next how we use it to obtain cipher. So let's return to the general format, but not mod 11, mod 5. We are going to have 3 at power 5 minus 1, which is 4 times k plus 1, congruent with 3 mod 5. With this particular relation, okay, we can observe that the applications for various values of k yield 3 at power 4 times 0 plus 1, it's 3 at power 1. For k equals 1, it's 3 at power 5. For k equals 2, it's 8 plus 1, 3 at power 9. For k equals 3, we get 4 times 3 is 12 plus 1, 3 at power 13. All of them congruent to 3 mod 5. Okay, so with these equalities, congruencies, we are armed now to look into this introduction to cryptography with Fermat Theorem. Note first that 3 at power 0 is congruent with 1. 3 at power 1 yields 3. 3 at power 2 congruent with 3 times 3, which it's 9 modulo 5. It is congruent with 4 mod 5. Three at power 3, 3 times 3 times 3, 3 times 4, which is 12 mod 5, it is 2. 3 at power 4 will be 3 times 3 times 3 times 3, which is 2 times 3, so it's 6, which is 1 mod 5. A question that comes out of here is an observation first. The results you are getting are all distinct. Namely, we get 1, 3, 4, 2, 1. Okay, so we get a repetition from this level on. So what we can actually use without repetition are the powers from 1 to 4. We get a repetition, in this case, each 4 exponents. And we can look at these exponents as keys in a crypto system. Namely, we could raise a message, in our case 3, at an exponent and get a ciphertext. All these ciphertexts look different. 3, 4, 2, 1. Would we be able to return backward from these numbers to the original message? In order to return backward, we would need to be able to use just this ciphertext, and let's take one of them. In this case, 3 at power 3. And we can note that it consists of 3 3s. In order to get if we know the key, that the key was 3, the exponent, and that the ciphertext is 2, in order to retrieve the message itself, which happened to be 3, all we need to do is to raise this ciphertext at power 3, which it's the same as raising the original message. Now, when we decrypt, we might not have known what the message was. We know that it was raised at power 3, raised again at power 3, and we get a at power 9, and this is a at power 4 times 2 plus 1. So we get back the message. In our case, raising 2 at power 3 gives 8, which modulo 5 is equal to 3. So we are able to retrieve back the message. Is there a way to retrieve the messages back if one would have encrypted the message with the other keys? If the key would have been 1, the message is already 3. So yes, for key 1 we don't need to do anything, but it would not have been a good encryption. For the key 2, we have the ciphertext being formed as the message squared. There's unfortunately no way to repeat our solution at the key 3, since there's no exponent to which we can raise this, no multiple of 2 that would lead to an exponent of the time 4 times k plus 1, because 2 is even, so multiply with everything will be even, cannot be 4 times k plus 1, which is the exponent that would return back the message. The same for exponent 4. It's already a multiple of 4 at any other exponent, any other processing of it would still be multiple of 4. There would be no way to get something that's a type 4k plus 1. So we would be able to retrieve a message back if the exponent was not 2 and not 4, was in this case not containing factors of p minus 1. So here we have a cryptosystem that can be inferred based on this, and the cryptosystem is called the Exponential Cipher. The way to encrypt with this cryptosystem is to first select a prime p, let's say 7. Select an exponent. The exponent has to be selected such that greatest common divisor between it and p minus 1 is 1. Let e in our case be equal to 7 to 5. 5 is relatively prime to 6. Or not many other numbers that are relatively prime to 6. And in order to decrypt, we are going to have to raise a ciphertext to a power d, compute it as the inverse of e mod p minus 1. In our case, 5 inverse mod 6, and we are going to use the extended Euclid algorithm, so we write 0, 6, 1, 5. 6 divided by 5, it's 1, remainder 1, and 0 minus 1 times 1 is minus 1. We arrived at 1, therefore the inverse is minus 1, which is 6 minus 1, 5. So the decryption in this particular case, decryption exponent is the same as the encryption one. So to encrypt any message, let's say x equals 2, we are going to encrypt it by raising it at power exponent, which is 5, getting 32, which mod 7 is congruent with 4. It's 28 plus 4 mod 7. To decrypt this message, the recipient of the message would decrypt 4 by raising it as a power d, which is 5. So we raise that power 5, which in this particular case it's the same as 2 to the power 10, known value, it's 1024. 1024 divided by 7 is 146, remainder 2. So this is congruent with 2, which is returning our message back, mod 7. What we can note over here is that this kind of crypto system does not give us perfect secrecy. In particular, there are multiple solutions, multiple not all possible decryptions, not all possible messages correspond to the ciphertext. In our case, the ciphertext was 4, but the only possible keys, mod 7, the only numbers that are relatively prime to 7 are 1 and 5. They are the only number relatively prime to 7 minus 1. So therefore, the only possible messages, if an attacker will try all possible keys, are in this case 4, respectively 2. So an attacker, even if it doesn't know the key, knows that the key mod 7 can be only 1 and 5, and therefore the only messages that can correspond to 4 are 4 and 2, and the messages cannot be 1, 3, 5, 6. As such, this solution is not offering perfect secrecy. Okay, let's take another example. If the prime was, let's say, 11, then E would be one of the numbers that are relatively prime to 11 minus 1 with 10. They are 1, 2, 3, 4 is not relatively prime with 10, so 3 minus 1 is 10, 5 is not relatively prime, 6 is not, 7, 8 is not, 9. Let's take E equals 5. Yes, sorry, equals 7 in this case, and then D has to be selected as the inverse of 7 mod 10. It's a number which, if we raise 7, we are the message, we are going to get a multiple of 10 plus 1. So while we multiply with 7 to get a multiple of 10 plus 1, and we again are going to use extended Euclid algorithm. 11 divided by 7 is 1, reminder. Sorry, this is 10, reminder 3, minus 0 minus 1 times 1 is minus 1, 7 divided by 3 is 2, reminder 1, and here we get 1 minus minus makes plus, 1 plus 2, 3. So the inverse will be 3, and our decryption key will be 3. Let's make an example with this value. So let's again take the message x equals 2, encryption of 2. It's giving us 2 at power 7, which is equal with 128, which is mod 11, which is equal to 1 plus 8 is 9, minus 2 is 7, mod 11. And decryption of 7 is going to be equal to 7 at power the exponent for decryption, which is 3. It's equal to 49 times 7, which modulo 11, 49 is 5 times 7 is 35, which is congruent with 2 mod 11, and we have retrieved back our message. Okay, so in general, as you see on the slide next to us in order to encrypt the exponentiation cipher. One selects the prime p, and one selects e, an exponent such that greatest common divisor between e and p minus 1 is equal to 1, such that the inverse d exists, where d is the inverse mod p minus 1. And then for encryption, one encrypts message x by computed x at power e mod p, and to decrypt a ciphertext we raise the ciphertext at power t mod p. The total number of possible keys is the number of elements e such that they are relatively prime with p minus 1. And as we are going to see soon, this number of elements has been studied by Euler and is smaller than p minus 1, and therefore the total number of messages that can be obtained from a given ciphertext is smaller than the total set of residues mod p, and as such this cryptosystem seen here does not offer perfect secrecy. The cryptosystem that we see here is the first number theoretic cryptosystem we study in this class, but it is not a public key cryptosystem. It's a secret key cryptosystem. The keys E and D have to be stored secretly by the sender and the recipient of the messages. If one knows E, it is possible to get D out of it, and if one knows D, well, one can get E as the inverse mod p minus 1, p minus 1 being also public, part of either the encryption or the decryption key. As such, the exponential cipher, it's a symmetric key cryptosystem, but it's a very important one, as with minor modifications we are going to see next, one can obtain a efficient public key cryptosystem. How would this cryptosystem be used? As we have seen before, prime would have to be selected. If the prime is small, the attacker can easily try all possible exponents for decryption, and therefore get a lot of information about possible messages. If the prime p is large enough, so if p very large, in that case so if p is very large, in that particular case we can have some confidence that an attacker will not be able to raise the ciphertext at all possible relatively prime numbers with p minus 1, and therefore some security, computational security is achieved, not perfect secrecy. And this is a typical case with this family of algorithms, even if with the following public key cryptosystems based on this exponential cipher. But this also raises an additional issue, namely how to find very large primes. And second, how to exponentiate the message at power e efficiently. Mod p mine. Okay, so these are complicated issues, and we are going to find the solutions to this. First, we are going to see the fast exponentiation algorithm, which allows these computations to be done efficiently for the person who encrypts and the person who decrypts the message. An attacker would have to do this many times for all possible keys because he doesn't know the key, and that's why the solution still remains the crypto system can be safe. The finding of a large prime will then be explored with several prime finding algorithms. And with this we conclude this lecture. And in the on-campus synchronous class we are going to discuss any questions you might have. Welcome.